Hello, today we're going to go through AQA Paper 1 Physics on radioactivity. To start with, let's just remind ourselves of what an atom looks like. So in the middle we have the nucleus, and then we have some electrons orbiting around the outside. And then within the nucleus we have protons that I've coloured in black, and the neutrons that I've left blank. The thing to remember is it's the neutrons that makes the nucleus unstable. There's too much energy inside, and it needs to release the energy, and that's what leads to radioactivity or the release of radiation. We'll start by going through the history of the atom. We'll start with Dalton, who came up with the solid sphere model. So it's a model where he identified that atoms were all very spherical in shape. After that was J.J. Thomson, and he came up with the plum pudding model. He knew the idea of charges, one was positive, one was negative, and he decided that within the plum pudding we've got the currents that were negative, and it was surrounded by a positive dough. But what he didn't realise was that it was the negative charges that could move, like the model that we understand today. Next was Rutherford and his nuclear model. He used alpha particles, which he knew had a positive charge, to probe through the atoms. He shot alpha particles through a gold leaf. Most of the alpha particles pass straight through, which suggests that most of it is empty space. However, some got deflected, and the reason they got deflected was because, as I said, alpha is positive, and they were deflected because the nucleus is positive because of the protons. And 1 in 10,000 roughly deflected greater than 90 degrees, and that tells us that the nucleus is also very dense. So once it hit it straight away, it reflected backwards. And then he also worked out that the radius of the atom was 10 to the minus 10 meters. And he also said that it's the electrons that orbit around the positive nucleus. That then brings us on to Bohr, and he said about the planetary model, the idea that electrons have specific energy states. So we've got electrons that orbit each shell, and each shell has a different value for energy. What can happen is the electrons can absorb energy and move to an outer shell, just like when you throw a ball up into the air, it will move away. However, the ball will have to fall down, and the electron is the same. However, when the electron falls down, it releases the energy in the form of radiation. It was said that each difference in shell was a discrete amount of energy. It was a certain amount of energy, and that related to the frequency of the radiation that is released. A consequence of all this research is that we can remember facts ready for our exam. So let's just go through the facts on this topic. There are 3 types of radiation: alpha, beta, and gamma. And you need to know about mass, the charge, what stops it, and how far it travels or its penetrating ability. We'll start with alpha, and as you can see, it's got 2 symbols that I've written. So first of all, more commonly, it's the alpha particle or alpha symbol, but in your exam you might well see it written He, because the definition for alpha is it's the nucleus of a helium atom. It has 2 protons, and the 4 on the top tells us the mass number, which is 4, but that means it's got the 2 protons, and then to make up the 4, it's also got 2 neutrons. As well as having a mass of 4, it's got a charge of +2. There are 2 protons, and we know that protons have a charge of +1 each, so it's +2. Neutrons have 0 charge. It's highly ionizing. That means it gets stopped by paper. It's really easy to stop. And equally, as it travels through the air, it will only go about 5 centimeters. A beta particle can be written 0-1 with a German S symbol, or beta, or get used to seeing it as an E, because actually a beta particle is a fast-moving electron. The reason it's a -1 is because within the nucleus, when beta particles are released, a neutron switches into a proton, and the fast-moving electron gets ejected away. Because a beta particle is just a fast-moving electron, the mass is very, very small. Never, ever say that it's 0. There is a mass, it's just very small. And the charge, well, it's an electron, so it's -1. About 5 millimeters of aluminium will stop it, and in air, it will travel around 1 meter. So it's a slightly higher penetrating ability than alpha, but grand scheme of things, not massive, certainly compared to the next one, gamma. Alpha and beta are both examples of a particle, whereas gamma is a high energy or high frequency electromagnetic ray. As it isn't a particle and is an electromagnetic ray, it will have a 0 mass and it has a 0 charge. It takes a few centimeters or more of lead or concrete to stop it. And in air, it travels an unlimited distance. It's highly penetrating, but not very ionizing. Let's focus on alpha decay next. So I've got an isotope here of thorium, and it has 90 protons, and the mass number is 228. And thorium, in this case, releases a helium nucleus, or an alpha particle. So what we have to do is work out what is left behind once 2 protons and 2 neutrons have ejected away from the nucleus of thorium. So if 2 protons and 2 neutrons is left, we need a number that's 4 less than 228. So we've got 224. Next, we need to look at the bottom number. So we know we started with 90, 2 get thrown out of the nucleus, which then means we've got 88 protons remaining. And then the final part of the jigsaw is choosing the element. In this case, it's radium. Although this will be given to you in the exam, so there's no need to remember that. So with alpha, the atomic number reduces by 2, and the mass number reduces by 4. So you've now done an alpha decay equation. Next, let's look at beta example. This time, I've got potassium, which has got 19 protons, and its mass number is 40. However, this one releases a beta particle, or a fast-moving electron. And again, just like before, we have to balance the equation like you would in maths and chemistry. We'll start with the top. We start with 40, 0 on the top leaves, so we're left with 40. Then we can focus on the bottom number. So here we've got to start with 19, but on the right-hand side it's minus 1. So we need a number, take away 1, that equals 19. So for calcium, it's 20. So the thing to remember about this is the atomic number goes up by 1, so it goes from 19 to 20, but the mass number does not change. It stays, in this case, at 40. A neutron has turned into a proton and released a fast-moving electron. The thing to look at is activity. So radioactive things, like rocks, will release a certain number of atoms every single second. So when we say activity, what we mean is it's the number of unstable atoms, the ones that contain too many neutrons, in a source that decay each second. Activity has a unit, and that is the becquerel, or capital B, little q. And 1 becquerel just means there's 1 decay per second, and that decay can be either alpha, beta, or gamma. There's no way of knowing. But the thing to remember is the activity reduces over time. A radioactive rock, as it releases more and more energy, it will then become less unstable. So as a consequence, over time, it will release less radiation per second, so we'd say the activity over time reduces. You may also have heard of something called count rate. So when measuring the activity of something, you've got to remember that there's background radiation as well. So the thing that you count using a Geiger-Müller counter would be the count rate. And then to find the activity, you need to take away the background radiation, the stuff that's all around us caused by cosmic rays or rocks that are releasing alpha, beta, and gamma in the area that you are. Next, let's look at half-life. It's the time that it takes for half of the radioactive nuclei to decay. We've mentioned the idea that activity reduces over time because something becomes less radioactive, and half-life is a measure of how quickly this happens. Something to remember, though, is that all forms of radioactivity and the release of radiation is a random process. We can judge how much radiation is going to be released, but what we don't know is which individual atom will release the radiation next. You'll often see half-life plotted in a graph like this. It will have count rate along the side and time along the x-axis. And the number to look for is the y-intercept just here, and in this case it's 100. So to find the time that it takes for the radioactive nuclei to halve, well, we know it's 100, we halve it to 50, we go across to our line, go down, and in this case the answer is 5 seconds. And we can double check that. Again, we can halve it, so 50 to 25, we can go across, and this time it's 10. So another 5 seconds have passed. So in this case, the half-life, it takes 5 seconds for the radioactive nuclei to halve. And different elements will have different half-lives. Some are very long, millions of years, others are very short, such as this one, in the order of seconds. All of the different properties of alpha, beta, and gamma, whether it's the mass, the charge, how far they travel, or the half-life, gives rise to dangers, but also uses. Something to mention, though, with dangers is ionization. So because they have a charge, in case of alpha and beta, it can lead to ionization. So that's when it forces cells, for example, to gain or lose electrons. They become ionized. And when this happens, it can damage or even kill living cells and damage and alter genes. So it can be highly dangerous. So to reduce the danger, what we need to do is limit the amount of time that we're exposed to the radiation. We can increase our distance so we can move further away, or we can shield behind concrete or some lead. However, there are some uses. So alpha particles can be used for smoke alarms. Even though alpha only travels a few centimeters in air, it's enough distance for it to travel between where it comes out from the rock and the sensor, and then there's enough gap there should smoke get in the way for the alarm to sound. Beta particles can be used to measure the thickness of things such as aluminium. If you have a really thick piece of aluminium, then only a small amount of radiation will be able to pass through. However, if it's a thin piece of aluminium, then a far greater proportion of the radiation will be able to pass through the sheet of metal. And then by knowing how much radiation can pass through, that can be linked to the thickness of the sheet of metal that you have in front of you. Gamma. That can be used for treating cancer, can also be used to sterilise medical equipment. So whilst gamma would be seen as dangerous, but you can also have some very useful uses of gamma radiation too. That now brings us to the end of the video. I hope you found it useful, and as ever, let me know if you have any queries or questions. Please also click on the link to subscribe to my channel. Have a good day.